everyone. Thanks for joining us today. And yeah, and welcome. And I hope the next 30 minutes is worth your time. I'm Felix, and I'm going to be talking about how to make KleidiAI work for your machine learning framework. So I don't really have the charisma of Steve Ballmer to get the audience to chant developers, developers. So I'm not even going to try that. But you understand like what I'm trying to say here. This talk and this session and KleidiAI is all about developers. And what KleidiAI does is it accelerates your machine learning workloads for best-in-class performance across ARM CPUs. Now, who's the primary consumer of KleidiAI? That's machine learning framework developers. And you'll notice here that, like I say, for use across multiple frameworks and not all frameworks, and there is a reason for that. I'll touch upon that as we go on. But if you're not a machine learning developer, if you're not a framework developer, then what is it in it for you? Like if you're an application developer. So the way to look at it is if we deliver the right optimizations in KleidiAI and the frameworks integrate it in the right way, then you should see performance out of the box. You can just focus on the functionality and not worry about performance. That is the end goal here. So in KleidiAI, we talk a lot about microkernels. So we'll touch upon what is a microkernel, and once we complete that, and then we'll go into the integration aspect of KleidiAI. So what is it? What do we mean when we say integrate KleidiAI into a framework? And we'll discuss some of the components there, and then we'll go into the individual integration aspects of it, like how do you integrate a packing microkernel and a main matrix multiplication microkernel. And throughout this talk, I'll be using a GEM or general matrix multiplication as an example. Microkernels. A microkernel is a building block to improve the performance. At a very high level, it's a building block that improves the performance of a machine learning workload. Now, what is the micro in it? It's a C file which has functions which has some optimized code in it, and it comes along with a couple of header files. So with 3 files, you can take those 3 files, put it in your framework, and get acceleration for your machine learning workload. So that is the micro aspect of it. And we also provide framework developers with tools and other well-defined interface for integration. And what are the tools that we provide? Again, we'll go through that in detail later. So that said, the way that we look at a machine learning workload is very different from how a framework looks at it. So if you're a framework developer, or if you're just dealing with ML models, you look at a model and say, you look at it as operators. I've got these many operators, I've got 20 operators in this model, and that's how a framework looks at it. So a framework would ask, how can my operator be accelerated by KleidiAI? But we don't look at it like that. So we look at it as, what is the underlying core operation of the operator? So what that does is it abstracts away all of the hyperparameters of the model, like if you take convolution 2D, it abstracts away like striding, dilation, and whatnot. So we look at it as, okay, at the core of it, it's a matrix multiplication. And so we find commonality with other operators in that process. So we look at it. So common2D has things in common with fully connected, batch mathmul, maybe a torch linear, and all that. They all have a matrix multiplication as its unifying factor. So that's a fundamental difference in how microkernels are seen. Now, let's put this into a workflow and see how it goes. So let's leave out the text for now. So you have a machine learning model, a framework or an optimization library consumes it. When I say an optimization library, I don't mean KleidiAI. I'm talking about a library like xnetpack, which can consume subgraphs. So you'll do your usual things, like you'll process your subgraph, and then you look at it at an operator level, do your memory management, and you'll execute it. You can schedule it, thread it, and all that. By the time the flow reaches here, your convolution 2D or batch matrix multiplication operator is now broken down into smaller chunks, and you, at this point, it looks like it's just a basic matrix multiplication. That is where KleidiAI gets involved. So KleidiAI, if it's integrated into the framework to handle matrix multiplication, will now process that workload. Now, we are not in this game to chase after operator support. A framework might support hundreds of operators, right? But what we are after is performance. So we are after the operators which are bottleneck in a network. So we just pick those handful of operators among those hundreds of operators, and then just optimize that. So there'll always be a fallback, or I would say, or the main path for operators that are not accelerated by KleidiAI for the framework. So you could think of it as a less invasive way of optimizing certain operators in your framework. Right. Now, integration components. So now we get into, now you know what KleidiAI is. Now we'll see what does it mean to integrate. So when we say, I want to integrate KleidiAI, what are the components that are involved in that? So the first thing is, you have to look at it as at a slightly higher level than at a single operator. One microkernel in the sense like one C file along with a couple of header files that it comes with, can be the performance solution for multiple operators. So the question is, how does the framework handle this? So this is a very rudimentary picture that I drew, but it tells you, for example, there are 4 operators here. You have the 1x1 com2d case, batch matrix, batch full connected, and LST. They all have matrix multiplication at its core. Ideally, what we want is, we want a single integration path in the framework where you pick the gem matrix multiplication, gem microkernel from KleidiAI, and you accelerate all of these 4 operators. That is what we ideally want. If your framework has to do one integration for com2d and a separate one for batch fully connected or batch matrix, that's really not a scalable solution. So we find the common part of it. We find multiple operators which need a single optimization and have a single integration for all that. So that would be an ideal integration case. So let's go through a couple of workflows where we'll go, on the left-hand side, you'll see a regular non-KleidiAI workflow, and on the right-hand side, you'll see a KleidiAI workflow. So this is for static input quantization. Let's say you have a matrix n by k, and the right-hand side a k by n or a n by k matrix. It's very common in the optimization world that you have your right-hand side is packed. The packing, we'll get into the details a bit later. And you have your optimized implementation. That's straightforward. Now your framework might do that. But some microkernels in KleidiAI, they require packing for the left-hand side as well. Now, this is something that your framework will have to add about as a new flow to the handling of operators. How easy is it to handle? That's up to the framework. So this is why the integration effort differs from framework to framework. For some frameworks, adding a new flow like a left-hand side pack might be a very straightforward thing. Whereas for some frameworks, it might be a more complicated task. So what I'm trying to say is like the integration effort varies. And but there are cases where it can be a very smooth one. Like for example, take the case of dynamic input quantization, where you already have a box which does the quantization of the left-hand side before the matrix multiplication is done. Now, in that case, what you can do is like you can just take out the existing quantization part and then plug it in with the quantize and pack part, because it's not a change in the flow or you're not adding anything new. You can think of it as you're just swapping one box with another. So the integration effort varies. That's the takeaway here. Now, that said, we have talked about packing, quantize, and all that. Now, let's get into the packing microkernels. So if you're not familiar with packing, it's a very common optimization technique where you arrange your weights on the left hand or the right hand side serially in memory so that you can exploit, so that caches can exploit the temporal locality. So, and in this, we'll go through. So, when we started KleidiAI, we had a certain idea of how we want the packing kernels to be. But as we integrated KleidiAI in multiple frameworks, we had to change. We had to adapt according to the needs or the requests or new requirements from the frameworks. That's something that we'll go through here. So this is the default case or the ideal case on how we started. So you have a gem microkernel, which comes with its own right-hand side packing function. And then you have a gem-v, vector by matrix microkernel, and that comes with its own different packing kernel. So you might ask, why do you have a different packing kernel for gem and gem-v? Well, a gem-v has just one vector, so the registry usage pattern is completely different. So that usually leads to a different packing format. But some frameworks don't like these multiple handling of different packing kernels for the gem and the gem-v. They look at it as, I want the same packing format for both gem and gem-v. And there is a point in thinking as you could argue that the bottleneck is not exactly the packing kernel, the bottleneck is gem. So, which is why if you look at our packing kernels right now, the format is common between gem and gem-v. And so how many packing kernels are too many? So the common cases, so you'll have the matrix multiplication microkernel is not a generic one in the sense it's for a certain block size. Now, if you have one for block size A, that would come with its own packing kernel. And then if you have a different matrix multiplication kernel, that would come with its own packing kernel. Now, again, this is how we would like to be ideally. And I like this format because if you look at the input arguments for this, you have an input pointer, output pointer, and probably the number of rows, 3 arguments, and you're done. You don't need any other information because this is a very specific microkernel. It knows the format that it's packing, and it's all good. But frameworks, again, might not want to handle different packing kernels because they want to focus on the center of attraction, which is the matrix multiplication, which is the bottleneck in your workload. So, which is why for some cases we go with a generic packing function, which takes in a lot more arguments than the very specific packing format, but that's how it is. And for some frameworks, that is the solution. And the ones that don't handle multiple matrix multiplication microkernels, we just go with a single specific packing kernel. At the end of the day, it's a trade-off. And a word about the API of these packing kernels. So you have 2 packing kernels, one for the left-hand side, one for the right-hand side. Left-hand side, I really like them because they're very simple. There's no, you just give the data, left-hand side data, and then you get something packed out, that's it. Whereas right-hand side, if you take right-hand side, you have a lot more data to pack there. So it's not just the right-hand side data. If you take a quantized int8 case, you have your bias, you have your scale, and if you're lucky, you'll just have 1 0 point, and then like you do things like you row sum for your gem-loki optimization and pack everything together. Now, earlier I said in the second slide I showed you, we say that KleidiAI supports multiple frameworks and not all frameworks. This is one of the reasons. So one of the things that we do right now is we pack all of these bias data, scale data, and all of that in an interleaved manner with the right-hand side data. Not all frameworks can handle that. So for now, there is, you could say that there is a limitation that some frameworks which can't handle that won't be able to integrate KleidiAI easily. And yeah, that's about the API. I think that concludes the packing section. Now we go on to the main metrics. How are we on time? Should speed up a little bit. This is the last section, by the way. Now we go to the main microkernels, which is matrix multiplication. Right. So right now we have around 105 microkernels in KleidiAI. And so you're a framework developer and you have an operator in hand, conv2d. You come to KleidiAI and say, I want to accelerate this. What do you have? You know, and we whip out a long list of options. It's like ordering coffee in some cafes, like where you're provided with 4 different beans and 6 different coffee types that goes with it, and a combination of vegan milk option and like cow milk with a few fat options, you know. Like, see, I take my coffee black, and like I'm stressed when I see the option list there. That's, it can be a bit like that, but then which is why we say KleidiAI is for framework developers. Because as a framework developer, you know what you want, you know the data type that you're interested in. Yes, it might be a long list of data types that you need to choose from, but you know what your operator needs. And then you know your quantization type, and you know if you're optimizing for a classic ML case or a generative AI workload case, where you'll be going to the dynamic inputs there. And then you know what your hardware is and what kind of extension it has. Does it have an i8mm or a dot product? And you select the right appropriate microkernel. So yeah, while it might sound like a lot of options, if you know what you want, you can pick the right one. Now, how many microkernels are too many? So when it comes to matrix multiplication, as simple as it is, there's no, a specialized microkernel operates on like one specific block size, meaning it's optimized for a certain block size. Now, you could just pick one microkernel and say, this is it. This is what I'm going to use for all matrix multiplication use cases. And that'll be your single microkernel. While it might be good for most, it might not be the best in class for all workloads, which is fine. But you might be a framework which says, you know what, like I'm going to cater to all my use cases and I want best in class for all use cases. In that case, like you need multiple microkernels, which also means it increases your integration complexity. Now you need to add a selection logic which selects microkernel A in case of use cases A and B, and microkernel B in cases of other use cases. So it's up to the framework to say what you want. And on the topic of how do you choose these multiple microkernels, there is no simple answer for that. You just have to let the numbers speak there. So this is one of the tools that we provide. We provide a benchmarking application. So if you have 4 or 5 models, bring in your use case, bring in your workload, split that into M, N, and K and into matrix multiplication blocks. Provide that as one of the inputs. And then let the benchmark application run and give you the results. And then based on that, you just pick the microkernel that you want. So there's no ambiguity there. So what you see is what you get. And finally, There are like few other additional information, like all microkernels expose scheduling arguments. So this will help you schedule or like break the problem statement into smaller pieces and work on that. If you don't want to use that, and if you want to provide the whole entire matrix as to the microkernel, that's fine as well. We can handle that as well. And the API for the matrix multiplication is quite consistent. There are 2 or 3 variations, but apart from that, it's the same. And GenAI use cases is one which introduces some variation on this. So, in summary, how do you go about it? If you want KleidiAI to be integrated into a framework, first, is a microkernel available? If yes, then take what you want. And select the right packing kernels. There again, you choose, do I want a specific packing kernel or do I want something more generic? And then have a single point of integration, wherein one microkernel serves multiple operators, so that you can get a wider reach coverage for your machine learning workload. And that is basically it. Any questions now?
What frameworks have you integrated Sorry. What frameworks have you currently integrated KleidiAI into?
So name a few. It's integrated in XtendPack, PyTorch. Nikhil here is going to talk about how KleidiAI was integrated into PyTorch. And you have Onyx Runtime, and yeah, and a few other frameworks. Any other questions? And if you want to discuss more about KleidiAI, I'm here the next couple of days. Please come forward and talk. Yes.
I'm interested. Are the packing kernels performance critical in the same way that the main gem kernel is?
It depends. Like if you're just going for the right-hand side, then it's not, because the weights are usually can be packed beforehand. But for the left-hand side, usually not, but it can be a bottleneck if it is not optimized. So if you have a highly optimized mathmul kernel, and then you have a not optimized left-hand side kernel, then we have seen that that can become a bottleneck. Then you definitely need optimization in that case.
So, full disclosure, I'm a compiler person, so I can't hit everything with a hammer. I wondered if the complexity problem that you talked about having a very large number of potential ways to plug into KleidiAI is something that CodeGen can help with. I understand that the core kernels having those hand optimizers is compilers are unlikely to beat that. But is there some part that code generation tools can play in making the scaling problem you talked about easier?
That would be quite interesting, yes. Yeah. Because ideally, personally, I would like to spend most of my time on the matrix multiplication and less time on the packing kernel. So anything in that regard, that would be great. We should have a chance. Yes. All right, time's up. Thanks again for your time.